Hey again, method students. In this section, we're going to be looking at confidence intervals. And the idea here is that, like, if you take a sample to kind of investigate something, to try to find something out about a population, well, the sample that you take might have a particular sample proportion, but a confidence interval is used to kind of like try to understand how likely your sample is to represent the population well, right? So like you might take a sample of a few different people from your school and find out that 10% of that sample is left-handed, but you're not really sure how well that would represent the population of the whole school. Well, a confidence interval can kind of give you an idea of, based on your sample, how well the sample will represent the population. So that's what we're essentially thinking about here. In terms of, these notes here, well, as the distribution of p hat is normal, we can use the mean and standard deviation to identify confidence intervals associated with p hat. And as I was saying before, these are important because we're interested in knowing how reliably our sample will represent the population. A confidence interval can be determined Z standard deviations below and above the mean. And remember that Z is like literally the value that means how many standard deviations above or below the mean we are. A Z value is like a standard score. We looked at those when we started doing normal distributions. The greater the value of Z, the higher percentage the confidence interval will be. So for example, Z equals 1.96 actually is for a 95% confidence interval. If we wanted to be 95% sure that our sample proportion is going to represent the population proportion. But if we wanted to increase that percentage, we would also increase the value of Z. In terms of what this might look like on a bell curve, well, it's kind of like saying, well, if here's p hat, if p hat is our sample proportion, the proportion that we get for a particular sample, that's going to sit right in the middle, and the distribution of p hat is, it's normally distributed. Our confidence interval can be found by starting from p hat and subtracting the standard deviation multiplied by Z. That'll be the lower end of our confidence interval. The upper end of our confidence interval will be p hat plus Z times the standard deviation. So we're kind of adding and subtracting the same multiple of the standard deviation on either side to give us an interval where we're pretty confident that the population proportion would actually sit within. All right, for a 95% confidence interval, and it's not the only one you'll have to do, but it's the most common percentage you would have to do. We actually will know that 95% of a standard normal probability distribution lies between Z equals negative 1.96 and Z equals positive 1.96. In other words, 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. And that's what that probability statement's saying there. The probability that Z is between negative 1.96 and positive 1.96 is approximately 0.95 or 95%. And since p hat as a variable is approximately normal, well, we get this formula here. This is the kind of the confidence interval formula, if you like, for 95% specifically. It says the probability that p hat minus 1.96 times the standard deviation is less than p, which is less than p hat plus 1.96 times the standard deviation. That probability will be approximately 95%. Or in other words, once we take a sample, we're 95% sure that the population proportion will be somewhere in between these two values that we work out using this formula. Okay, we can actually generalize that too to say, well, if we want any particular percentage, maybe we want 99% confidence, or maybe we only want 90% confidence or something like that, then this is the formula that we're going to use. And it's almost the identical formula, except instead of this 1.96, we're going to have a different value, and that's what's written as Z here, right? Where Z is something that we're actually going to have to work out. So again, though, you can see that it's really p hat minus Z times the standard deviation. That's our lower end of the interval. And then the upper end of the interval is p hat plus Z times the standard deviation. In these cases, we just have to actually work out the value of Z first, and we'll go through an example of how to do that. Okay, let's give this a go with a couple of practice questions. So example 1, in a sample of 500 voters, 120 have indicated that they will vote for Labor. Find a 95% confidence interval for the proportion of all voters who are predicted to vote for Labor using Z equals 1.96. All right, so let's start by trying to work out what our sample proportion is, our p hat. Right, and in this question, p hat is equal to, if this is the proportion of people who are going to indicate they're going to vote for Labor, then in this sample we have 120 out of 500, which, let's do it as a decimal, oops, is 0.24. So that's our sample proportion. Another way to think of it is like, 24% of this sample have indicated they're going to vote for Labor. We're interested in knowing, like, well, how confident are we, or what do we think that does to apply to the actual whole population, the whole country or something like that, like how many people are actually going to vote for Labor. So our task here is to find a 95% confidence interval for the proportion of all voters who are predicted to vote for Labor. So we're going to use this formula. We've been told to use Z equals 1.96. And so we're going to say, well, the lower end of our confidence interval is p hat minus 1.96 times the square root of, now p hat we worked out was 0.24. Hang on, sorry. Should have put 0.24 here at the beginning. 0.24 minus 1.96 times, so we're just inputting the values into this part of the formula. 0.24 times, and then it's 1 minus 0.24, so that's going to give me 0.76 over n, which is the sample size, and in this case the sample size is 500. Okay, so that's going to give us the lower end of the interval. All right, now it's absolutely a calculator question, so let's carefully put that into the calculator. We have 0.24 minus 1.96 times square root of 0.24 times 0.76 divided by 500. We get 0.20256. Now the question I think said to 3 decimal places. Yep, so we're going to write that as 0.203. Okay, now the next part, I'm going to write it out fully, but the next part is actually quite easy because all we really have to do is the exact same calculation, but we're going to change this minus to a plus, right? Because we're just trying to find the upper end of this interval, right? Which is the exact same calculation, but p hat plus z rather than p hat minus z. So we've worked out our lower interval, our lower end point of the interval. Now we're going to work out the upper end point. Exact same calculation, but with a plus. All right, and that will equal, and again, you can kind of save a bit of time on the CAS. If you want both numbers to still be there, I'm just going to drag that down, but change that minus to a plus, and get 0.2774, so to 3 decimal places, that's 0.277. Okay, so our 95% confidence interval is from 0.203 to 0.277. Right, and what you should always notice is that these two values will be kind of equally far apart from p hat. So p hat is 0.24. That sits like right in the middle of these two values. That was our sample proportion. But based on this particular sample, we would be 95% confident that between 20.3% and 27.7% of the population are going to vote for Labor based on this. In other words, we know the value of p hat, and we'd be 95% sure that the value of p, the population parameter, would be between these two values. That's what the confidence interval represents. All right, let's try another one. And this time we're going to be looking at a different percentage. It's not a 95% confidence interval, so we're going to have to work out that Z value. Okay, so here, from a sample of 50 adults, it's found that 75% of them completed year 12. So we've got our n equals 50, and that's a sample proportion, so p hat equals 0.75. Okay, we've got to find a 98% confidence interval for the proportion of the adult population that has completed year 12. Answer in percentages correct to 2 decimal places. So our sample suggested that 75% of people completed year 12, but we want to actually get a confidence interval for how accurate that's going to be. So for a 98% confidence interval, let's start with that. We have to find this Z value for 98%. We want to know what is Z going to equal. There's a couple of ways to do this, but I think the easiest way is to do it as follows. We're going to use the inverse normal distribution because we're essentially thinking about, we want an interval where we want to know how many standard deviations either side of the mean do we have to go to get 98% of the distribution. In other words, I don't want to make a mess of my page too much here, but in other words, we're kind of thinking of it like this. We're thinking of, well, if this is p hat, and that's a symmetric normal distribution, well, the value of p hat that we found, that should be capital P hat, the value of p hat that we found here was 0.75, but what we want to know is, like, if I go to here and go to here, and I want 98% in the middle, right, like what values are here and here? But if we think of it in terms of Z, well, then it's really, think of it in terms of Z, then really the mean is 0, right? And the standard deviation is 1. And I want to know, well, how many standard deviations below and above the mean are we? So, you know, this might be, in the previous example, it was negative 1.6 and positive 1.96, but that's now going to be different because we're talking about 98%. So we're essentially kind of imagining this situation, and we're going to try to find these two values. Easiest way to do it is using inverse norm CDF on the CAS. And so we go like this. We go interactive, distribution, inverse. and then inverse norm CDF. And what we're going to do is we're going to say, again, there's a couple of ways to do this part, but I'm going to say, let's choose the tail setting as center, because when you look back at that pretty rough sketch that I did, we're looking at the middle, right? This sort of symmetric part in the middle being 98%. So I'm going to put the tail setting as center. The probability is 0.98, 98% of this proportion in the middle of it. And the standard deviation is 1 and the mean is 0, because we're finding a Z value. And remember, Z is the standard normal distribution. The standard normal distribution has a standard deviation of 1 and a mean of 0. So you leave those two numbers as they are. And you hit OK. And the CAS is somewhat limited here. It'll only give you the negative value, right? But the positive value is just the same number here. So really what we're, same number without the negative sign, really what we've just found, if we can get them both on the screen there, is that this number here is Z equals negative 2.32 and the rest. This number here is Z equals positive 2.32. Okay, so now we've got our Z values to use in this formula. It's negative 2.32 and positive 2.32. All right, so we've got it. We've got Z equals 2.32 and so on. Okay, I'm going to keep that number, the full number in the CAS to make sure it's nice and accurate. And so we can say, well, now we know our Z value, right? Let's actually go to the formula. There's this formula here. Oops, yep, there it is. Right, so we're just going to put Z and the P hat and the N all into this formula and find our confidence interval. So we've got the confidence interval is, now you can set your working out, like in the previous example, we found the lower end of the interval, then the upper end of the interval. You can set it, I find that the best way to set it out. It's up to you if you want to kind of go straight into the brackets, but let's just say, let's do the lower first. That will be, so using the formula, oops, off the screen there, doesn't help. Using the formula, it's P hat, so 0.75, minus Z times, so I'm going to write 2.32 ... times the square root of P hat times 1 minus P hat, so that's going to be 1 minus 0.75, which is 0.25, divided by N, which is the sample size, 50. All right, and that is going to give me the lower end of the interval, right? So working that out gives me the lower end of my 98% confidence interval. So let's plug that in carefully. It's going to be 0.75 minus, now instead of just writing 2.32, I'm going to actually use the whole number there, times square root of 0.75 times 0.25 over 50, and that gives me 0.6075. What did it say? 2 decimal places. So actually, sorry, it said as a percentage to 2 decimal places. So really, I need to, as a decimal, I need this to 4 decimal places. So 6075. Oops, it's off the screen. 0.6075. So that's our lower end of the interval. The upper end, remember, it's actually the exact same calculation, but with a plus. So 0.75 plus 2.32. Right, so you're not going to type it all into your calculator again. You're just going to go, I'm just going to hit execute so it repeats the calculation, and then change the minus to a plus to get the upper end. 0.89245, so 0.8925 to 4 decimal places. So we've got our lower and upper end of the confidence interval, right? But we're asked to answer in percentages correct to 2 decimal places. So the 98% confidence interval is 60.75% to 89.25%. Okay, so in other words, for this particular, based on this particular sample, we would be 98% confident that the population proportion is somewhere between 60.75% and 89.25%. All right, already a pretty long video, so I might cover the rest of it in a separate video. I'll see you on the next one.